Uh, Good evening, everybody. Welcome to our mid-month meeting. And today we've got number one. We got Peter, who's going to be discussing understanding phase noise, and then Dave's going to talk about a topic of interest: documentation of test procedures. Then an update for the Pro project and an update for the Backplane radio project. But before we get started, got to read the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. And now that that's all done, Peter, take it away.
Wait, didn't you forget the land rights acknowledgement and the radio rights acknowledgement too? The spectrum is a tradition.
Keep going, Hassan. I'll kick you out of here.
Okay. Wait, did
Peter, you're muted if you're speaking.
Right, you are. Can you hear me now?
Yep. Yep.
All right, that's off to a good start. And can we see that?
Yep.
Okay. Understanding phase noise. What is it and why it can be a problem, and can we do anything about it? It started off as just basically what I'm saying here, just to understand it a little bit better, because I really didn't know what it was all about. And of course, now that we've been dealing with some noise stuff, I think I'm learning a little bit more. So I'm definitely not an expert on this particular subject, but let's see where it goes. So basically, as we all know, oscillators are in the phase noise. The phase noise is a measure of the short-term instability of an oscillator's output signal, and it quantifies those fluctuations in the phase of the signal as it is referenced, of course, to a stable reference signal. So in our ideal oscillator, which is usually purely sinusoidal signal, they describe it mathematically as what you see in the screen. And amplitude is the A of the oscillator output. And the radial or angular frequencies, I'm not sure what they pronounce that, W anyway, is a constant as well. The radial frequency typically refers to the frequency at which the phase noise power spectral density is measured or specified. I thought I understood this, but now I'm even more confused about it since we've been doing these noise measurements of late with the probe. And phase shift or phase offset is also constant. And then this is just a pictorial, it's just showing, a clean signal, no phase noise, no jitter. And that's the ideal world. So with the non-ideal or the real world stuff, there's the equation for that. And basically it's the same equation, except now we've added, two ways. We've put both the amplitude and the phase offsets are now a function of time. And you can see the results of that, where you can see the jittering in the sine wave. And then, of course, in the time domain or in the frequency domain, you can see the skirts have now spread all out. So this phase noise is a term used to describe short-term variations in phase or frequency stability, and random and unintentional phase modulation. And while short-term stability or good phase noise performance is important, the short-term stability can be difficult to obtain. And it's usually substantial cost and complexity is associated with only modest increases in phase and noise performance. The most common effects of phase noise are spectral regrowth, which causes decrease in sensitivity and selectivity and increase in bit errors.
Peter, there's some background noise there somewhere.
Yeah, just hang on a sec. I'll be right back. Why are we being awful? I'm doing a presentation. I'll get this in the background, please. Sorry about that. Okay. So the review of mixing. We all know this, but just to make it a complete, the complete story, and we'll just go over it quickly. Spectral regrowth and decreased sensitivity, selectivity are both related to mixing. And the mixer is a device that's used to move signals from one frequency to another, blah, blah, blah. And it's used in receivers for two main reasons. We're easier to work with lower frequency signals than higher. And mixing allows the use of fixed frequency filters, amplifiers, etc. In other words, like the IF. So the figure 3 there, we just see your typical signal of interest over here on the left coming into your mixer with your local oscillator, and it's nice and clean. And this is, we all know this is what your output is, the plus and the minus, etc. So, and any phase noise in the local oscillator is now also mixed with the input signal. And this results in the mixing products that are now distorted and spread in frequency. And this is what's sometimes called spectral regrowth. And you can see in the same scenario, the incoming signal it looks like that, but your oscillator or LO is got some phase noise in it, and then this all mixes in it, so you can see your sum and your difference frequencies now have included the phase noise from the LO. So this what can happen when you have the spectral regrowth. When you look at the say your channelized frequencies, and you can see how in the worst case scenario, this picture is one channel is now wiped out, or one signal is now wiped out the 4 adjacent channels. Now some are a little bit lower. It's not as bad as that. That would be an extreme, but you can see how phase noise can be a problem. Okay, phase noise can cause problems due to reciprocal mixing, and reciprocal mixing arises in situations where a small wanted signal, this one here, is adjacent to a large unwanted signal in the red. And we have a clean oscillator, LO, and everything's happy, mixes properly, and our IF filter can handle the rejecting the large unwanted signal, not a problem. However, if you have a noisy LO, you can see here now where the sensitivity of your and selectivity of your system is now compromised, and you can see here where the wanted signal is just peaking above the phase noise, and just blew it up here a little bit so you can see a little bit clearer. So this is why, or this is how that happens. So there's two types of test gear that we can use to measure phase noise: spectrum analyzers and phase noise analyzers. And with the spectrum analyzer, the big advantage is it's a general purpose instrument. You can use it for other things. It is the traditional tool for measuring phase noise, and it's usually performed by means of a phase noise measurement application, which I didn't do or use. And then there's the phase noise analyzer. And I didn't really look into that too much, but you can bet that they probably cost a small fortune, probably significantly more than a spectrum analyzer. I'm guessing, but I bet it is. And then again, you're talking about now you've got a something that you don't use a whole lot, that's very expensive. So with measurements using the spectrum analyzer, the steps, power of the carrier, we'll call PC. So you measure up here, and then your noise power, you measure that within a 1 hertz bandwidth at a given frequency offset from the carrier. So here's where your offset is. So it's important that you define the offset along with the figure that you come up with. And then you subtract the carrier power from the noise power, and that yields your LOF in units of dBc per hertz. So they generally will, by convention, make the measurement at the positive frequency offset. But phase noises are usually symmetrical around the carrier. So if for some reason you can't measure on the positive side of the carrier, you can probably have no problem doing it from the negative side. But like I said, from convention, they take it from the plus side. So in summary, phase noise describes the short-term variations of the frequency phase signals produced by oscillators or other devices. Phase noise measurements are used to quantify the phase noise performance, and the results are typically given in a single sideband plot, which shows the phase noise as a function of carrier offset. And then here's an example up here. On the top right is a single sideband phase noise plot. And on the bottom left is spot noise. And then this is just a little chart of the spot noise. So you can either get it like that, or you can get it like that. And your carrier would be up over here. So let's try something a little bit on the practical side of things. Industry standards. So they seem to be all over the map here, and some of them are so wide that I don't even know why you'd even want to make a measurement. But anyway, for what they do here is for low phase noise oscillators, the near carrier offsets such as 10 hertz to 100 hertz are critical to use. And for communication systems, the offsets range from 1 kilohertz to 10 kilohertz. And high frequency stability systems, offsets from 100 kilohertz to 1 megahertz might be used. But in practice, 10 kilohertz is often the standard offset for general purpose phase noise measurements, especially for RF or communication systems. But, whenever I look at phase noise, not that I look at it a lot, but what I have seen there, boy, you don't have to go anywhere near a megahertz and it's all gone in the noise. So when I was doing a couple of measurements, I was within a kilohertz of the carrier. So I took the Siglant 1032X and made some measurements there, and I came up with through the steps that I just highlighted, and I came up with a number of minus 79.8 dBc per hertz. And I thought, well, okay, that's pretty good. It seemed too easy, but that's what I came up with. And I thought, well, let's see how else they do it. So I started to look into other ways of how how industry calculates phase noise. And this was what I came up with. And so the first thing you do is you convert the carrier power to watts, you convert noise power to watts, you normalize noise to 1 hertz, and then you calculate the phase noise, and you can see all the math that's in behind that. And I thought, oh, okay. So the figure used was 10 megahertz at a 50 hertz offset, and measurement bandwidth, you can see the numbers there, and the carrier power minus 27.8. Anyway, you do all that math that's highlighted on the right, and you come up with minus 63.2 dBc per hertz. So I thought, okay, that's an interesting thing to do. Oh, and I got this off of ChatGPT, by the way, for full disclosure. And I thought, well, there's no way in a million years I'm going to do math like that for that figure. So I said, so ChatGPT said, would you like me to do write a script, a Python script to do those calculations? And I thought, sure, why not? So it did that, and it worked great. So I ran it. It took me about 10 minutes to figure out how to get it to work properly, but it did. And then, of course, here it is, the answer. And it spat out the 63.2. So that was a much better way of doing it. But still, to me, it's a bit of an awkward way of going. So I decided let's go back to the way that I first described, nice simple calculations, and let's see what that number comes up with instead of doing all those conversions to watts and normalization formulas. And I took those same numbers, 10 megahertz, 50 hertz, etc. And I went through the power of the carrier, noise, power within 1 hertz bandwidth, blah, 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 subtracting it all up. And guess what? I came up with the same number, minus 63.2 dBc per hertz. So I'm not sure why they lead you down the garden path with all that complicated math when the very simple one yields the same results. I'm sure I'm missing something, but anyway, that's what we came up with. So ChatGPT, thank you. It was interesting, but I don't think I'll go that route at all. And that's just where I was just plotting out the phase noise on my signal generator. And you can see I went out to 1 kilohertz on that case. But there is a problem, and there always is in this game, isn't there, eh, guys? Noise power calculations are assuming that the filter is a boxcar. In a spectrum analyzer, the filter is Gaussian. And the rule of thumb is to assume 20% is missing. And I thought, okay, that's interesting, but I didn't bother factoring in the 20% that was missing in my calculations. But just be aware of it. So in conclusion, what can we do to minimize the phase noise? Well, really nothing. When I originally started to put this together, I started to do all kinds of thinking, okay, well, what about analog filters and audio filtering? Can we do something there? Sharper IF, all this kind of stuff. You always come back to thinking, no, really there isn't. I put an asterisk beside the digital filtering because, they do some pretty interesting things with algorithms. And Drew will probably remember one of the breakfasts we had. Somebody was talking. I can't even remember the full what was going on there, but there's some algorithm was really cleaning up background noise and whatnot in RF reception. So, maybe in digital filtering they might be able to do something. I'm not sure, but that's way above my pay grade. And really, the only thing you can do is select the low phase noise components. But like I say, that can be an expensive option. And maybe all the stuff that we kind of do, it's not a huge deal anyways. But, in the end, we do have a better understanding of the phase noise. So now we have a little bit more of a complete picture in the noise that we hear and, less unknowns in the makeup of overall noise. And that's all I got, guys. Thank you.
So when you're on the air and you hear noise, how do you know whether it's phase noise or just atmospheric noise?
Good question. I don't know. I think really you'd have to start listening to it and then try to understand it better. And to be honest with you, I didn't do that. It might be an interesting thing to try is to create some phase noise and then listen to it into the receiver.
Okay.
But being aware of it, just to kind of go back, when you're having problem with selectivity and sensitivity and things like that, maybe you might want to track down and you'll take a phase noise measurement of your LO and maybe you might find that there's something going on there. Instead of thinking it's just atmospheric noise, you now know that, well, you know what, maybe it's not. Maybe there's some phase noise going on in there as well.
Yeah. Is jitter considered phase noise?
I believe so, yes.
Yeah. Okay, so that would be like you're looking at your scope and you're looking at signal, and once in a while it jitters over to the left or right.
Yeah. Where is it? Right near the beginning, I think it is. Yeah, you're talking about like right here.
Yeah.
If you got lots of phase. See, this is in the time domain, and this is in your frequency domain. So this is what the phase noise looks like in frequency domain. And if you put your scope on this, then this is what you're going to see in your scope, and that's what you see with your jitter.
Yeah. Okay, we got Dave. Go ahead.
Uh-oh.
Yeah, the hypotenuse of the inverse trilateral. No, Peter. It just, you got me thinking. I think phase noise is everywhere.
Yes.
I don't think you can get a really good, because I remember looking at the specs for our SIGGENs, which is a high quality signal, arbitrary signal generator, waveform generator, and it's got phase noise. So I'm just wondering what's acceptable. Is there any idea of what's acceptable? That obviously none, but that's not the real world.
No, Dave. You know what? I never thought about that. What's acceptable in phase noise, and I in the readings for this, I never came across where they even talked about that. But that's a good question. I think I'm going to make a little note there and just see if I can find something. I guess I mean, I guess really, what's an acceptable phase noise depends on the circuit that you're building, right? Or the signals that you're processing. If your phase noise is too excessive, like that one pictorial I showed, where it it can wipe out your signal, right? Or it can make it very difficult to see. Like in here, if you had this issue here, you could say, well, you know what, the phase noise in my oscillator is, or the stability of the oscillator isn't good enough, right?
But how real is that? Like, if you got that much phase noise, I'm just, you know, talking out of my butt here. But if you got that much phase noise that's going to wipe out, your signal, yeah, that's a problem. But how do we know? Like, if we're listening, we built a radio, we're listening to it, and at what point do we listen to it and say, oh, this has got a problem, I better go check the phase noise? That's kind of what I'd be interested in, is how does this apply to the real world?
I think the way it's kind of like the way I was answering with Ken. If you were having a problem, say I think the way we would notice it is not so much noise in the background because you're in signals, but let's say, for example, you had trouble with, you found your selectivity and sensitivity for sure, is somewhat lacking. Then you might have to go in and maybe you don't know what it is yet. So maybe doing some testing on your LO might reveal that you've got a lot of jitter going on, or phase noise that's going on in that LO. Now, what's causing it could be, either a crappy component or something else is going on, right? Otherwise, I'm not sure how. Like when Ken asked, how can you tell by listening to it? I'm not sure you can. Maybe you can. I'm not sure though.
Yeah, because I guess the issue is, okay, if you kind of look at the forest from the trees here, you've got a signal, okay, and you've got another oscillator that you're going to mix that with, okay, and as you said, they mix and you get all kinds of wonky components, right?
Mm-hmm.
But at what point, is the mixing going to be such that it's going to harm the signal of interest you want?
I don't know.
Can I take that?
Yeah, have a go.
So Dave, you're coming at it kind of backwards, right? Like, but you really do this from the design spec when you're starting to build the thing. What's the sensitivity you want of the receiver? How much phase noise can you tolerate? Then design your circuit to produce less than that amount. Measure whether you're producing less than that amount or not, and you're done. If it deteriorates over time, if you find less sensitivity, you're starting to lose signals in the background noise, then maybe run it through and test again and see if maybe the root cause of that is phase noise.
Okay, so then I'll re-ask my first question. I asked, how do we know how much? You said, okay, we're going to design a radio and we're going to have a certain selectivity, certain sensitivity. How do we know how much phase noise that we need to have that sensitivity or to have that given selectivity? Do you understand?
Well, but that goes into your budget, right? Like one of the specs in that will be the signal to noise ratio. So then you decide how much of that noise can be phase noise, and how much is coming from thermal noise of components and so on. Like you have to do the whole analysis, or put a wet finger in the air and make it as good as you can and live with it, right?
But that's what, to your point there, Charlie, now that I've read up on phase noise and done this, now you piques your interest and you might go down that rabbit hole just to see. But so far over our HB careers, all we've done is we've taken standard parts that every ham uses to build our circuits, and we've just accepted what we've got, what we get, right? We've never sat down to design a board thinking, okay, what's selectivity and all this kind of stuff and in sensitivity that we want, and that means that might drive a certain component that has a certain amount of phase noise to it. We've never designed a circuit with that kind of thinking in mind, right?
Well, but But that's because we're mostly copying commercial circuits and either
Right.
simplifying them or changing them. The
Right.
commercial guys do this analysis. They spend the time and, crunch all the math and figure out what their objectives are and design the circuits to meet those objectives.
Yeah, that's right.
But you go to school for a few years and get your RF engineering degree, and you can do this stuff, right?
So I'm going to ask another question now. Peter, go to your slide where you show the measurement of phase noise. Like it's the slide that shows like the dBc relative to like 1 hertz.
This one?
Yeah. Okay. So there, you're seeing your phase noise is giving in a signal of dBc per hertz. Okay. That's because you see, I'm confused. Okay, I get dBm. dBc is a power measurement, but it's a power relative to the carrier. How much lower the power is to the carrier. How does that translate to noise? Because to me, spectral density is the amount of power that's in the noise. But this is a dBc measurement. How does that translate to noise? Do you see what I'm asking?
Well, I think what they're doing is they're quantifying this number right here, right? This level.
Yeah, because I get what Charlie's saying is that this is adding, it's adding to the noise. It's changing your noise budget. If you've got a signal to noise ratio, and you've got so much noise that you have to tolerate, this is going to add noise to it. My question is, how do you know how much noise it's adding? Because these units don't match. There's got to be some other way of doing this. Like there's got to be a way that you could translate the phase noise measurements in dBc per hertz to a true noise spectral density or noise power density. Because dBc per hertz, that's a noise power density. That's not a spectral density. If it's spectral, it'll be square root of hertz.
I can't answer. I can only. I'm basically regurgitating what I read, right? So
yeah. So anyway, that was my question. Let's not, go down a rabbit hole here. But just curious to see how. Come back to what Ken was saying about how do we know how this is going to impact us? And I guess Charlie answered that to say it's going to be part of the overall noise we're going to get.
It'll be part of all the noise.
yes, true.
Can I jump in? It's Michael.
Yeah, go ahead.
I was wondering, I'm thinking, how does this relate to what we're doing with the noise measurements for the probe? And we never talk about this offset thing at all.
No,
that's not part of our discussion. And
but this is different. We're measuring the noise floor levels or what noise we're contributing to the overall. Where this is just measuring what they call their phase noise at a specific offset. But we're looking at it from a broad sense.
Yeah, I guess looking at that graph, the midpoint of that blue vertical triangle or rectangle rather would be some measurement of the noise relative to the carrier, wouldn't it?
That's what you subtract off of the carrier.
Yeah.
Figure.
And we're just not talking about offset at all, but it's buried in there somewhere. Yeah. Okay. That's fine. That's what I wanted to ask.
Right.
Yeah, Michael, noise. I could speak about white noise. If you look at white, the reason why it's called white noise, because white's made up of a whole bunch of different colors, right? So noise, if you look at a white noise, it's made up of all frequencies. So if you measure at a certain frequency, the noise is going to be basically the same. Not necessarily true. The noise may change in frequency, but ignore that. Let's just say it's the same. So because the noise is spread out across all frequencies, you have to look at the density of noise. you have to take a sample and say, okay, in 1 hertz, how much is my noise in 1 hertz? So it doesn't matter. I know that if I have 10 kilohertz, I'm going to have 10,000 times the noise of 1 hertz.
Yeah. Okay.
Whereas, like on this one here, you're not measuring the white noise, like the noise that Dave was talking about raises the whole floor level up, right? Whereas we're just measuring a specific small area, the noise that's been generated, or in this case, the phase noise, and then you're doing a particular offset, because you can see, depending on what your offset you pick, your figures are going to change, and that's why when you talk about phase noise, you have to also declare the offset.
I guess if you were to take, if you took the graph here and you sort of integrated somehow all the noise under the curve that's going down and to the right, that would be the average noise, the white noise.
Well, no, this is just strictly phase. This wouldn't be the white noise. See, like this is like when you do it, you get a plot like this. And then and sometimes you'll just quote it. What they do is a spot noise, and you pick a certain this would be your frequency down here. So you're looking at a certain offset. So in this particular case here, with this one particular carrier, if you quoted, the offset at 1 kilohertz, there you're at 98, minus 98 figure. And if you're 100 kilohertz away, you're at minus 127. So that's what I'm saying. You need to declare what offset that you are taking your reading at.
Okay.
It's a big difference if it's a big difference if you and I are doing this and I'm quoting this figure here and you're quoting this figure here, and we're wondering why can't we get the same results? That's why.
Okay. Yeah.
But I think Michael, I think you're on the right track. Now that I think about it, Peter, go back to that chart with the where you got the little blue 1 hertz. I think Michael's right. You have to, because if you look at the noise there, it's got nothing to do with the carrier. You're just relating the noise relative to the strength of the carrier.
Yes.
The lower that carrier is, the worse your signal to noise ratio is, kind of like, right? But I think Michael's right. You have to look at all the noise under that chart there, because it's at different offsets, you're getting less, you're getting a worse signal to noise ratio. So you got to figure out some way of taking an average, integrating over that whole thing.
And I'll bet you if you did that, you might find that the overall noise level relative to the carrier could conceivably, I don't know, be halfway up that peak. If you did those, like where the L brackets T is, the overall noise level could be up there. Who knows? We don't know, but conceptually, maybe that's what it's all about. I don't know.
But if you're trying to resolve, say, I'm just going to make up a number. Say you want to resolve 10 hertz off of the carrier. You got some signal, and you want to get it 10 hertz off the carrier. Well, on that chart, 10 hertz off the carrier has got a much worse signal to noise ratio than, say, 1 kilohertz off of the carrier.
Yeah. And that's why I was saying in here, you can see for industry practices for low phase noise oscillators, the near carry offsets, they use like 10 hertz to 100 hertz because those systems are critical. Whereas down in RF, general RF areas, in practice, they may go 10 kilohertz.
Well, that's what the second bullet says, doesn't it? Yeah, that's right.
So it just depends on what they're doing.
Yeah, okay.
Howard's had his hand up for quite a while. Go ahead, Howard.
Yeah, thanks. It's good discussion, Peter. Sorry, I missed the first part. And my one question was answered in the discussions that just had. But my second question was jitter. If you have a frequency display and the last digit jitter, is that the same jitter from phase noise, or is that something else?
I'm not sure I follow the question. What do you mean by the last digit?
Well, sometimes you see where there's a frequency display and they'll say no last digit jitter. Like let's say it's a 100.4, and that 4 will go like 3 or 4.
Oh, I see.
Is that the same thing, or is that something different?
It could be from the way I'm thinking and the way I understand this stuff. It could be just the way your scope or your measuring tool is measuring something. Maybe it's because the number of reads it's doing and the signal's a little bit different. So it could be a little part of the jitter going on because there's gonna be phase noise in anything and everything, right? So
Can I take a stab at answering that?
Sure, of course, please.
Okay, so Howard, what I suspect Peter's right when he says it's how it's being measured. Let's take a conventional signal, a frequency counter. Typically, you count a certain number and you multiply it, or you divide by a number. You got to divide by n or something. There's some kind of wonky divide or multiply that you're doing. If you've got a fraction and you're doing a divide, you lose that fraction. So if you've got 13.2, and you do a divide, you could lose that 0.2. Or if you multiply, you could lose that because that could add up to 1 hertz. So by doing that math, you lose that precision of that last digit, and that's why your digit is going to jump around. You're going to get that last number jumping around. It's a math round off.
Right. It's like the number of counts kind of thing.
Yeah, and so when you do the math, you do a multiplication divide, you're not accounting for that the 0.5 or 0.7. The other thing, it could be quantization error, because what happens is that if it's a ADC and it's converting the signal into a digital signal, you'll see all ADCs have a quantization error, and they'll say plus or minus 1 bit or half a bit. And so what that means, when it quantizes it, you get a number, and that last bit might go up and down, and so you might be off by 1 or maybe it might be worse, and the last 2 bits might be off, and that's going to add a lot more error, right? So Peter's right. It has to do with how it's being measured.
Right.
Does that make sense?
All right, that makes sense. Thanks.
Yeah.
If I can comment, it's Michael. The picture on the left of this diagram, with the sine wave variation, you see that all the time in an oscilloscope. When the signal you're trying to measure is too low for the scope to resolve it properly, you see this kind of stuff going on. If the signal sort of waves back and forth, jitter, exactly like that. I've seen that anyway.
Yeah.
Yeah, but if you got a scope that has automatic setup, it should compensate for that.
Oh yeah, you can get around it, but if you're actually looking live, so to speak, rather than getting it to do the auto set or whatever it is, it moves around. And I noticed before I had the SG1032, I had a much less expensive signal generator, and it didn't have the sensitivity, and you could see this stuff much more easily with that. You couldn't resolve low level signals as easily. Anyway, yeah, okay.
Yeah, if you have an analog oscilloscope, for example, and you see this jitterness going on, you can actually trim the trigger point.
Yeah,
and that should clean it up. But I don't think phase noises. You can do that with phase noise. It all depends how severe it is.
It also depends on what's causing it too.
Yeah.
Mm-hmm.
You can also turn on averaging on your scope, and that acts as a low pass filter, and so it'll filter out some of the noise. Mm-hmm. So then you'll get a much cleaner signal. I use that all the time. I average almost everything to try and get rid of the inherent system systemic noise. Like if your signal's got noise, uh, averaging might fix that, right? But I'm talking more the instrument trying to lock onto it and it can't.
Mm-hmm.
If you average, your instrument is going to lock onto it much easier.
Yeah.
Correct.
Yeah. Okay.
Okay. So, anybody have any questions or comments for Peter? Okay. Very good, Peter.
All right.
Interesting.
Thank you.
I'm sure it's going to grab some rabbit hole people.
Well, if I wasn't busy with other things, I might have a stab at it.
Yeah. Okay. Next up is Dave. Topic of interest: documentation of test procedures.
If I could jump in here, I'd like to say Dave's done a lot of work on this stuff, and his documentation is just excellent. It's really easy to understand. So for whatever that's worth, thanks, Dave.
And you're muted, Dave. Or did he walk away?
No, I got to find.
Oh,
I got like six browser windows open plus other windows, and navigating to the relevant one takes a few seconds at my age. So I kind of got pigeonholed into doing this. I just kind of suggested
A self-inflicted wound, I'd say.
Since I was the one that did the pigeonhole, I thought as a sort of a lead off, Dave, and then as it's a general conversation for all of us to try and participate.
Yeah, I get that. But I was just saying, the reason I got nominated, well, I got voluntold to lead this. But no, what I had, the problem we were having with the probe project, we've got our probe, but we're leading into the probe status a little bit. We've got a probe, it appears to be working. It appears to be working better than what we actually anticipated, and we're trying to quantify it. We're trying to measure it to see what the specifications of this is, and we kept getting values all over the place. And it's because we weren't measuring things consistently. We weren't tweaking, as Hassan would say, you got to go and tweak the knobs and see what you get. But we weren't all in sync with how we were tweaking the knobs. So then I decided, you know what, maybe I'll just write up some procedures of how I make certain measurements, make that available to the group, the probe group, so that they could use that as a template to say, oh, okay, Dave tweaked this knob and he turned this off and then he pushed this button, and that's how he made his measurement. And that way someone could come back and say, no, Dave, you shouldn't have pushed that button and you shouldn't have tweaked this button. You should have done this. So to come with a standardized way of making a measurement, I thought this would be a good practice for all of us to do if we're making some kind of measurement, especially the nano VNA. Most of us have it. We measure, we typically measure antennas or like a filter. You go and there's tons of videos showing you how to do that. But how do you use it to measure, something more complex? So if we're in a situation to do that, we could document that and make it available to everyone. And Kevin raised a really good point to say, okay, well, the ultimate goal is to have those procedures, but then have a script that we would run that would go and set up our equipment and make the measurement for us. That way, we are consistently making the same measurement each time. So that's kind of where it was at. So I'm going to open the floor to have comments, suggestions. Do people think this is a good idea? Is it something that's a waste of time? Is it a good idea? Is it something everyone could use? Because not everyone has the same equipment that we have.
I'll have a couple of thoughts, Dave. And again, just to reiterate what Michael was saying, the documentation that you've done on these procedures are second to none, Dave. They are so handy. They've given me some more food of thought, because part of the problems I've had is when I sit down to do some of these tests, I start off kind of winging it. And of course, when you do that, you make mistakes, or I would think I was finished. I'd turn around and I'd sit down and start to record all the, crunch the numbers. Then I realized I forgot something, or I did it the wrong way, and have to start all over again. So having some written documents is a good way to go. One thing that might be handy to add into these things, and it'd be easy to do, would be spaces to put in as you're going through these procedures, setting up your equipment and making these tests. It might be nice to have in black and white in the document to say, this is the value that I got. So that might be something we can work on later. I know not necessarily you, Dave, but I'm just saying it's a thought I've had. And the other one thought I've was thinking about is to where to store all these documents. Now I'm thinking, converting them to PDFs, of course, and then we could put the PDF, we could put them up on our website, so they'd be available to anybody and everybody. That's one thought I had. And I had another idea. What was it? Escaped me. Dave made mention we don't necessarily all have the same gear, but I think whether you have a spectrum analyzer or a tiny assay, that kind of thing, the procedures would be the same. Maybe the numbers might be a little bit different, and that you push or a button might be a little bit different, but it's sort of like this is a roadmap, if you will, and it should be useful for not just a singlet. Okay, these are singlet centric, but doesn't mean it's not applicable to another manufacturer's piece of equipment. Anyway, there's my thoughts.
It might be interesting to take the tiny assay and just try to duplicate some of the stuff we've done in the Siglant. I don't know. If you got nothing better to do.
Drew, you had your hand up.
Well, I was just thinking about what Dave said with the tiny assay and the nano VNA and the value of a script to reproduce the measurement, and I think that's brilliant, especially coming at it from my point of view, which is not from your point of view, which is what you're doing, and I don't necessarily. And just learning from the script alone would be of great value.
Knowing what you're doing is an illusion.
Well, I've often found that, but that's mostly my wife's opinion.
But I think, Drew, the question, and this is what I was saying, not all of our equipment can fall into that category. I don't know whether you can write a script and run a script on the spectrum analyzer. I don't know if that, the nano VNA. I don't know if that scripting is possible. I know with the signal and gear we've got a interface, and we can write Python. There is an API where you could write a little Python program, and it makes calls to set up and read the equipment. I don't know if such a thing exists.
I don't think so.
Nano VNA.
No, no, you're quite right. I don't believe it's that sophisticated, and I would hesitate to enter into its program. Yeah, no, it is not that sophisticated.
But that's the wrong use of the word script, right? Like, Drew, when you were talking about a script, you were talking about a set of instructions, step one, step two.
I was, yeah. Well, it's the old radio man in me.
Go ahead, Howard.
Oh yeah, I just had a question. But is the goal to be able to equate, like to make all the measurements the same, or is just the goal to quantify things in a consistent way? And if one person puts the information in from a tiny assay versus another puts it in from a real assay, is the goal to make the numbers the same despite what you used, or just to present them in a consistent way to understand?
Well, let's separate. I think, Howard, we first have to separate the conversation about automating the measurements versus documenting how we make the measurements. So, for example, if we have a procedure that shows you how to use a nano VNA to go and measure something, right? When it comes time to you to go and there comes a time where you have to make that measurement. Instead of you going trying to figure it out yourself, you could go to that reference doc, right? Go through it, and it'll explain to you how you do it. So I think that's the first stage, is to get to that level. Automating measurements, I don't think we're there yet. I think we're quite a ways away from doing that, because that's going to take a lot of time and a lot of effort.
It makes sense.
Go, Pete.
Yeah, I agree with Dave. The automated parts is a ways off, and we're fortunate enough that Kevin is intrigued about this rabbit hole and is going to probably take that task on. But like I say, I think it'd be a little bit of a ways away. But in the meantime, documenting these noise, like for example, like Dave already alluded to, and of with these procedures, okay, like I say, they're siglet centric, but at least now that who's making these tests, we're all in different locations, and now we're on board making these measurements all the same way, and so our figures should be relatable to each other. And what we don't have really is, I know there's a couple of tiny essays out there, and there's some VNAs out there. So the people that are using them, if you're going to go measure your antenna, maybe record the steps that you're using to make that antenna measurement and document it. And then now we've got, this procedure laid out. And so that if anybody, especially like for me, I borrow Howard's VNA to make a measurement. So of course I have to break out the Coles notes or the manuals to even go through it and sift through all that stuff to be able to use it. So to have a bit of a cheat sheet would be a nice handy thing.
Go ahead, Michael.
I think the documentation it helps me to make sure that I what I've used so far, to make sure that I know that if I do it right, I'm going to get the same results as, say, Dave and Peter, more or less in the ballpark. I think things like nano VNAs, likewise, if you had it's all very well to say, well, there's YouTube videos out here on how to do X, Y, and Z, and you can spend, of course, hours looking at YouTube videos and trying to figure it out. But the idea of having a PDF, step 1, step 2, step 3, whatever, it makes it a lot easier to go through and hopefully get things right. I think that's my thought on it anyway.
Go, Pete.
Because let's face it, a lot of times these measurements that we're making, we don't do them every day or every week. So right now right now some of these measurements are imprinted in my head. But you know what? Once we stop making these particular measurements, it won't be long before you kind of lose it and say, okay, how did I set that up again? You don't want to go through the trial and error of making, these adjustments to get down to where you were or where you thought you were. By having a document there, now you can just quickly go to that document and then set up your instruments to make the test that you're after, and then follow a procedure of it. And Bob's your uncle. No. But again, do you think the website's a good place to store their stuff? Anybody got an opinion on that one?
Store where?
On our website.
Yeah, we could.
Oops.
You're talking about storing PDFs or something similar.
PDFs. I don't think you can. I think you can do JPEGs and PDFs on the WordPress. Anything else, I think you have to pay for. You have to pay
the plugin.
So the only thing documents we can put up on the website would be a PDF.
Yeah, and the other thing too, like for example, me, I'm on Windows 11. I don't have a Microsoft license, so I can't open a document. PDF is you know everywhere, and if you need to, you can extract the document from the PDF.
Yeah, and what you're after is getting. My thinking is what you're after is getting in the right ballpark as other people who do the same things, whether that ballpark is 10% or 15 or whatever, as long as it's not an order of magnitude out or something that proves to
Yeah,
you as you're doing it that you sort of know what you're doing. You can pretend you know what you're doing.
yeah, like the tiny SA or the nano VNA, they're not going to be as accurate as a real SA. But if you
Mhm.
can repeat it and get close to what an SA and it's repeatable, good enough.
Yeah, that's right.
Go ahead, Pete.
I think what really highlighted this is, and actually, if you go back to our SNA project, things got highlighted back then as well, because what's ended up happening is you're having 3 or 4 guys doing prototypes and testing of a project, and you're getting way different results. Now, this particular time, and that's kind of what was happening. We were all making little different settings on our instruments, and that's enough to skew, if you will, the results, and you're kind of left wondering, well, what's the difference? Oh, well, I had the preamp on. Oh, well, I didn't. These kinds of things. So
Yeah,
these things get quickly highlighted in a team in a team project. Now, as an individual on your own doing your own thing, it probably doesn't come to light. But when you think back on it, how many times have you sat and like I said, you'd be sitting there, you'd be making measurements, and you think, oh shit, I forgot something, or I didn't do it right, and you didn't realize it until after you shut everything off, or you wasted half an afternoon doing it, right? So it still becomes important, even for the individual.
yeah.
Anyway.
Okay. Anybody else have any questions or comment or anything? Very good. Thanks, Dave. Um, Now, I believe Michael, you're going to do an update on the probe in the backplane.
Yeah. Very briefly, as far as the probe is concerned, we're getting down to the short strokes supposedly, and as much as we've got a common board that we're using, and we're sort of validating things and using this documentation, and hopefully getting the results that they're pretty good. They seem to be all in the same ballpark, which is what we've been talking about. So, and this is prior to we're using a board that Dave put together that has a whole bunch of different amplifiers and whatnot on it, and we're getting to the point now where once we've done this testing and we're all happy with what we've got, then the next step would be to build a board that could actually be put in a case at some point. So we're getting to the point where we're going to be finalizing some things, given that we sort of know what the specifications of what we've got are. So that's the probe. As far as the backplane, I guess Charlie's done a lot of, well, Charlie particularly has done a lot of work in figuring out how the backplane should be laid out, different options as to numbers of traces and whatnot, and how to connect, how big the backplane has to be. The JL PCB size is 100 by 100 millimeters. It's possible to go bigger, maybe with not a hugely extra expense. So there's some work to be done to figure that out. And also we're starting to look at daughter boards, like a power supply daughter board that provides, from an external power supply, provides the various voltage levels we need. And also that would be a board that plugged into the backplane, and also various other things. Wayne's looking at filters, for example, and whatnot. So we're getting there. So that's sort of the status of that. It's not, I guess it's probably not as far along as the probe, well, it isn't as far along as the probe thing, but it's a longer term project anyway. So that's really where we are in broad strokes.
Okay. Excellent. All right. Dave, today you posted something about your Z80. You want to just do a quick discuss on it, if you can?
Not sure. Are people interested in that?
I am.
Okay, I wasn't planning to, but yeah, no, I'd been working on building this homemade homemade computer for, I don't know, almost a year now, and here it is. Here, it's got a backplane, and it's got all these boards. All these connectors are just connectors going between the boards that are not run on the bus, and it runs off of a SD card disk. So the SD card plugs in there, it boots CPM off of that disk. CPM's a really, really old operating system, and it's got a RAM, ROM, it's got memory, it's got a clock, it's got an I/O. Then at the front, it's got you can see all the LEDs here. Those little white things are LEDs, and they display the status of the bus and the status lines and all that kind of stuff. And so it's running CPM, and it's using a STM32 as the disk controller. And so that it works. It's just a matter of putting it in a case. So what I started to do now is I started to create a front panel. So that's kind of the front panel there. It's going to have a whole bunch of switches, just like the IMSI computer, or the Altair, the PDP-11, the Data General Nova. All these computers had switches where you could go and hand assemble. You'd put in instructions, deposit it, and then make it run. So it's going to have, that's what this is meant to be. And so you could then single step through instructions. And way back in the 80s, I, watching war games and, hearing that iconic voice, shall we play a game? Greetings, Professor Falcon. I bought the chipset that does that robotic voice. Back then, that was the only way you could do speech synthesis. And it's very poor, very robotic. So I've got that chipset. It's been sitting here since I got that back in like 88, maybe. So it's been sitting here a long, long time looking for a home. So I figured what I'm going to do is I'm going to build another board. Once I get the Z80 working, build another voice synthesis board, plug it into the backplane, and I can have it talking.
Cool. Yeah, I remember back in high school, I forget what grade 11, it would have been about 77, 78. And the physics teacher was talking to me, and he brought up the fact that the school had an IMSA kit. And he wanted to know if I was interested and putting together. Now, it didn't have all the discrete parts or anything, but it did have the case that had all the boards and everything. There was another teacher in another department that was also interested in doing it, and I really didn't say anything to them. And then one day the kit disappeared. Nobody knew where it went. So that blew my chance of trying it out.
And there's all kinds of kits now you can get. You can get like an Altair 88, I think it's 8800. You get an Altair kit which looks identical to an Altair, and in the back it's got an Arduino. So the Arduino is what's the term where you take cross assembly, not cross assembly, but you interpret the assemble code. You take the code that the Z80 runs, and then you interpret that using the Arduino code.
Yeah.
Yeah, you don't assemble it; it's doing it on the fly. It's
Yeah.
actually doing it on the fly. So it
Yeah.
knows that if you've got, as Z80 instruction saying increment, A, it's going to say, oh, that means increment blah in Arduino speak. So it translates it, right?
Or binary emulation or binary translators.
Machine
Yeah.
language, machine code.
Yeah, it's binary emulation or translation of machine code.
Yeah. See, also too.
And so,
no, go
yeah, I
ahead.
was going to say you're getting a lot of those systems coming out where they're actually running. Like I've seen one that's actually a PC. It's got a bona fide PC in the back, and it's running the front plate. Looks like a PDP, but it's actually a PC in the back of it. So you're getting a lot of kits like that now.
Cool. Yeah, I know. When I went to college, 79, there was the college was just getting into these little mini computers and stuff, and there was a night course on how to use a Z80, and I was able to take the Z80, read a keyboard, and read one of these big humongous disk drives and the old school liquid displays. And everything was done on a proto board with wire wrapping. And that was so cool. And everything was in machine language. Everything. So that was a good experience.
That's a big thing now. Is that, well, I shouldn't say it's a big thing. It's you're seeing a lot more of that style where people are building breadboard computers, and I think Ian actually built a 6502 breadboard computer. He was showing it, and it's the same one that Ben Eater. Ben Eater's got a channel. He's the one. I think he's one of the ones that kickstarted this whole thing. And now a lot of people are building 6502. 6502 is the processor that was in the original IBM, not Commodore PET, Atari, the original Atari consoles, all those computers. A lot of them had a 6502. And so you're seeing a lot of people going back to that. Because 6502 chipset is still available. Z80, they just stopped printing it. So you cannot buy any more Z80s chips. Whatever is out there, that's it. They're not planning to restamp it.
Yeah, I noticed that there were on some of these, like eBay, AliExpress, whatever, you can see a lot of gadgets like frequency counters or signal generators, and they're using the 6502. And there's lots of them around. The chip is available everywhere. Alrighty, that's a cool project, Dave. Um, anyways, we're approaching the witching hour. Does anybody have any questions, comments? Do they have a topic of interest you want to discuss? No, I guess not. I don't think we really have time for what's on your bench.
We usually do that at the mixer, anyways.
Yeah. Go ahead, Dave.
Yeah, I've just got one question. I don't know if anyone has any experience using something called the Y factor method for measuring noise. Has anyone looked at that? I don't know, Charlie, have you? I think you're probably the only one that's even come close to that, or Hassan. I don't think any of us will, you know,
Y
be.
parameters, right? The scattering matrix, is that the one?
No, that's where you take a calibrated noise source, you feed it into your device under test. It's got a well-known noise level, right? You know exactly what the noise is. It's like a calibrated, signal source, right? But it's noise. It's generating white noise or shock noise or whatever type of noise. You feed it into the device under test, and you measure what comes out. And apparently, you do that a couple of times or something. I don't understand the process myself enough. That's what I'm asking. Like, is anyone familiar with how you use that to measure noise
It's
of a
been
device?
it's been like 40 years, but I think it's basically measuring noise with and without a known noise source, because with the known noise source, it raises the noise floor up higher. So sometimes, if you're in a digital system, for instance, quantizing will eliminate the noise for you. And as soon as you bump it up a level, now suddenly you can see, oh, okay, it's actually my 10 dB of noise is now 10.5, so I've got a 0.5 dB contribution from my circuit, as opposed to trying to measure 0.5, which is within the quantizing error of your digital system. You can't really measure anything there. It comes up as zero, right?
See, I tried kind of doing that, Charlie,
Mm-hmm.
and I'm not getting what I expect, because I would think, okay, I know I'm feeding in a noise level of 1. I'm coming out, output coming out, I'm getting a noise level of 10. So therefore, I've got a tenfold increase in noise. But that's not necessarily the case. It's not linear like that. And if you look the Y factor, they do all kinds of calculations. They convert the noise to temperature and all this kind of shit. And like, it just boggles my mind the amount of math they're doing around this. So I don't know why you have to go through all that math. I would think it's just a simple, measurement, but it turns out that it's not a simple measurement.
Yeah, got nothing. Like I say, it's been 40 years since I played with that stuff.
Yeah.
Take a look at EMRFD. I think Wes has a chapter on that.
Okay, maybe that's a good, because I was looking. It's a funny story. It popped into my head. Why don't I just build a noise source? And so I went looking for a noise source, and I found a schematic that was posted online from EMRFD.
Yeah.
So so there's probably something there about noise, right?
Yeah, I know for a fact that Wes has got a circuit in the book.
But I'm not interested, because it turns out our signal generators has a noise waveform where it'll generate white noise for us. So it's the calibrated noise source. So I've got that. I don't need to build a circuit. It's just, how do I use it, and the math associated with it. That's what I need clarification on.
Well, take a look at Wes's book and see what. I seem to remember something going on in the book. I think there was a chapter or half a chapter or something. Okay. Anybody else have anything?
Yeah, he does talk about it. You're right. In the EMFRD, it's there.
What's the chapter number?
Well, it's all over the place, but in chapter 2 is a good start. Now, whether he talks about the Y method, I don't know. I'm just saying, yeah, there is something there. Exactly what it is, I don't know. I can't read that fast.
I might have an answer for Dave on that. Can you hear me, Dave?
Yeah.
So I think the reason they do that magic, they have like a hot noise source and a cold noise source. It's kind of related to this thing called the Dickey radiometer. The reason is absolute noise measurements are tricky because you can never have a noise-free measurement as a baseline. So what they do is they do differential measurements all the time. So your system has noise, and your noise sources have noise, but they're all unknown. And your measuring equipment has noise. So how do you deal with all that? Um, well, you do two measurements, one hot, one cold, and then somehow it comes out in the wash. So if you know the delta between your hot and your cold, that makes life easier because now at least the measurement is somewhat same. Because
But I think what I see a lot of them doing, Hassan, is they do a plot. They take the hot and cold and they draw a straight line through it and they extrapolate it, and where it crosses the y-axis, that's your noise that the system um, introduces for your device under test. I think it's something like that, but they have a calculation where they go about it, and I think they're just basically calculating the intercept, but they always go and translate it into temperature in Kelvin, and I don't understand why, because I don't get it. I'm
yeah,
like, why not just use power?
it's easy because you work at room temperature, but if you're making a guided missile, let's assume this is all because of military requirements. You're you're building a guided missile or a tank that has to operate during a nuclear war or in the Middle East or whatever in high temperatures. It has to be temperature compensated, and so you can't. Otherwise, your circuit will just fail if there's an explosion nearby or it gets too hot. So that that's the problem. That's the reason. And like we live at room temperature, so we only have one temperature in our minds, and so we can just deal with one set of measurements. But they're doing this, in the field, so temperature has to be factored in. And I guess when they extrapolate to the y-axis, that's kind of like extrapolating to zero temperature, and that kind of maybe makes the calculations more invariant. Remember, a lot of these techniques in the 50s and 60s were designed to save paper and slide rule time. So they really wanted one number they could print and give to everybody, and then you could just scale it. We live in a different world. We like for us, computation's nothing. Brain power is expensive, but they were trying to save on computational power. The stuff they did may not be necessary, but they just did it that way.
But I just wish I could find this is where the whole thing of a procedure comes in. I wish I could go open up a book and magically there's a page that explains this, and I don't have to read the whole friggin' book to understand it. That's my problem, because a lot of these you go, there's a white paper written on the Y factor method and it's like 20 pages long.
Right. Oh, I know.
Like
I get it. I've been looking for 20 years,
one
Dave.
page summary.
I've been looking for 20 years to see a proper description of all this stuff, and it doesn't exist because most of these white papers are just designed to reflect the state of the art that's existed, which is no longer the state of the art, but they have to explain the way it's always been done. If you want a true bottom up description of this, you're probably better off looking at YouTube. There's probably some genius there who's done it.
Yeah, been there, done that. Yeah, the thing is too, Hassan, if you look at some of the higher end spectrum analyzers or the higher end network analyzers, they do noise measurements, and you just basically push a button and it whirs and beeps and burps and it does the measurement for you and it spits out a number. So they've got automated ways of doing this, but you're going to have to spend probably $50,000 to go get the equipment to go do it, right?
You could, but If you want to find a real, I mean, you're with a physics background, look up Dickey radiometer. So he designed this thing to do really low, ultra precise noise measurements of radio signals from space, and that'll teach you. There are some good web pages I've seen about that, and that'll teach you the ultimate measurement, and then you'll see that the engineering measurements are just a subset of that, or a kind of a compromise, and it's easier to understand the physical perfect measurement than the other ones. Um, the other thing you can do is buy some liquid helium, go to absolute zero, and then never have to deal with noise again.
I like that idea. Then our noise measurement problem is over once and for all.
Right.
back back when I used to work around liquid helium, we used to go. You see people smashing roses. Well, we used to do running shoes. We used to go and say, okay, how far could we take this? Could we freeze a cat? No, we never froze a cat. We never froze a cat. But like we were doing some like roaches and all kinds of stuff. We were
Oh,
just
that's
crazy.
oh, that's
To
that's.
be young and in grad school.
At least you didn't try it on yourselves.
Stick your finger in there.
Darwin Award. But yeah, like noise is kind of one of those things where if you can observe it, you'll understand it. But if you read about it, it makes no sense because it's such a, it's purely a practical problem. So you might as well just do some measurements. I think the key thing is that noise spectral density and bandwidth are related. So when you measure your like 1 millivolt of noise, that's because there's something with like a, 1 microvolt per hertz noise spectral density, and you put a 1 kilohertz bandwidth on it, and you end up with 1 millivolt of noise. And so that's why if you build an RF circuit with narrow bandwidth, the noise is always better. And that's kind of one of the key things to remember. Like some of these physical processes generate noise in a funny way. They don't generate absolute noise levels, they generate noise power spectral density. It's spread across the whole spectrum. And the energy in that is kind of maybe constant, but the noise is spread over the entire spectrum. So when the moment you filter it, you reduce the noise, you throw away most of it. That was a hard thing to wrap your head around. Um, but the thing is,
Yeah, and even
yeah,
I found, Hassan, just having the way you screw on your SMA connector.
yeah,
If it's not tightened to a certain level, it adds. You see all kinds of stuff in the spectrum, and that's why I think you see people with torque wrenches when they're fastening their SMA connector is just to reduce all that noise.
The
that's right.
the IMSA guy does that, and I saw that on his webpage. And my brother has a 3D printer and made some little wrenches that have they're sort of standard material, but you push it too far and it stops torquing, like it slips, and that's the way to get a consistent pressure on your hex nut or whatever. So
Well, on Dwayne's blog, he's got a design that for 3D printing a torque wrench.
now that I think of it, that's where I got it from. I think I gave it to Peter and he did it. That's how I found that. That's right. I remember that discussion now. Yep.
Yeah.
Didn't Ian do something as well back when we were at uh, what's his face's office for our meetings?
Yeah, Ian gave us a bunch of these torque wrenches.
Yeah, I
Yeah,
think so. I seem to remember something.
yeah. Yeah, in the early days of radio, noise was easier to understand because, the spectrum was clean and your neighbor was the noise. I mean, the second guy who built a radio was the noise for guy number one. So now we live in a different world. We'll never see that noise-free world again.
No, our neighbors are still noisy.
Yeah.
Cool. righty. So if anybody, no one else has anything to discuss, questions, we can call it a night.
I think we should end with a noise acknowledgement.
Okay, somebody mute sound, get rid of the noise.
Okay, one man's noise.
Oh, he just cut my microphone. Thanks, Dave. Anyways, okay. So everybody, thank you for joining in the meeting. Have a good night and have a good weekend. And we'll see you on that will be April. It'll be the 9th of April.
9th, I think it's 2nd, isn't it?
Oh, sorry, 2nd. 16th is the regular meeting. Yeah. Okay, good night, everybody.
Yeah, good night.
Thanks,
Yeah.
Ken.
Take
Thanks.
care.